Welcome back. Yesterday we left off talking about electric potential energy and electric potential. Along the way, we've discovered or come up with a new idea or a new unit of energy. And the reason for that is because generally when one itty-bitty charge moves through a electric field over a distance, the amount of energy that that charge gains is relatively small. And so normally our units for energy, normal units, are joules. Okay? And so relatively though, if you're talking about moving one elementary charge, which has a charge of 1.6 times 10 to the negative 19th coulombs. And let's say you're going to move that through a voltage of 1 volt. And so in order to find the potential energy, your potential energy, actually let me change that to the actual unit we want, that potential energy, W, is equal to Q times V. And so that would be 1.6 times 10 to the negative 19th coulombs times 1 volt. And so your energy would be 1.6 times 10 to the negative 19th joules. Well, to get around that, we actually use a unit of convenience. And that unit of convenience is called the electron volt. And so if I slide up, it's this EV, okay? And basically, it's the amount of energy gained as one elementary charge moves through 1 volt. And so that energy, that W, is equal to 1 EV. And so really, really simple, and this is the reason why it's so convenient, is the fact that if you want to find your energy in EVs, you literally take the number of V's, you take the number of E's, and you multiply that by the number of V's. And so if I ask you to find out the energy that 2 elementary charges get when they move through a voltage of 4.5 volts, you would just go 2 times 4.5, oh, 9 EVs, done. As opposed to going 2 elementary charges, okay, well, that's 2 times the 1.6 times 10 to the negative 19th coulombs times 4.5 volts. It just gets more complicated. So just know that the EVs is a unit of energy, but it's a unit of convenience. And for the record, and this is on the front page of your reference tables, but 1 EV is equal to 1.6 times 10 to the negative 19th joules. Now this, okay, our joules is still our SI unit of energy. We still have to use that for our calculations when we do other stuff with it. But again, EVs is a nice short way to do it. Now, got it right here. Hey, equivalent to 1.6 times 19th. Equal number of V's times number of V's. I covered that for you. Now, this is also something that if we want another potential energy at some point, okay, we got to know where it's equal to 0. If we want to find that potential energy, it would normally be equal to Q times V. But let's say you don't have that uniform electric field. This V is only good. Because where we did before, V is equal to E times D. That's only good when I have a constant, E. If we don't have a constant E, then we have to go back and use our Coulomb's law. Remember that W is equal to the force times the distance. And so our force, that's we get from Coulomb's law, K, Q1, Q2, all over R. Yep. And so we're going to multiply it by a distance, and that distance is going to be the same as R. Oops, let me change this. That distance is going to be the same as R squared times R, which we're going to use R for the distance instead. So our electric potential energy is K, Q1, Q2 over R. Now, if we want to find that in terms of the voltage, remember voltage is equal to energy divided by the charge. So then we would take that W, that K, Q1, Q2 over R, and then we would divide that by Q. And so we can now have a way of finding our voltage, our electric potential, around one single charge as being this. Now again, for our purposes and regions, we will probably never use this, but kind of like the one I explained to you in class yesterday, this is kind of similar. We may, if you move to a higher level of physics, you may end up using this. Now, here's the next big thing, Okay, and this is we're going to start using transitioning from our theoretical and our informational and hey, here's our background stuff to actually usable stuff. But potential difference and charges, we have seen that if we have a positive charge here and we have a negative charge over here, that if I take a single free electron right here, just chilling out, that electron is going to have a force on it and it's going to cause it to go flying away from the negative and towards a positive. Okay? And these things are going to go flying. Now, what happens, okay, if we put a conductor, and I will put the conductor in a blue pencil. Wow, that really didn't show up well. You know what? I'm going to change that to an orange pencil. That's a little easier to see. If we put a conductor here, remember, conductors allow charges to flow easily through. What's going to happen is all of those charges that are in that conductor, that are just chilling out, that are easy to move, are going to get pushed away from the negative and towards the positive. Okay? And so they're going to get pushed away from that. Okay? These two things, okay, when they have different charges, remember we have defined ahead, there's a difference of potential. Or a voltage. Between those two. Okay? Those charges are going to flow until we have reached equilibrium. We have been in balance. Remember, when we talked about this when we were charging objects, either by conduction and induction, everything wants to be in balance. We don't want to have this difference of potential. Okay? And so what's going to end up happening is those charges are going to go flying through. I'll put it back in green. They're going to go flying through. Charge movement is going to happen until there is no longer a difference of potential. So what is end up happening here, okay, is that if these things have different concentrations of potential, or sorry, different concentrations of charges. So here's our positive, here's our negative, and we have this difference of potential here. There's a voltage between them. If you put a conductor in, I'll put that back in the orange because that's what I used before. Here's my conductor. Charges will flow until there is no longer a difference of potential. If you maintain that difference of potential, so remember, anytime an electron leaves here, leaves the negative, it's going to become more positive. Anytime that electron comes back over here to the positive, it's going to become less positive until eventually these two will balance. When they balance, electrons no longer flow. So if we had a way so that every time an electron came over to the positive, if we could magically move it back, I'll call it a magic electron mover. We're actually going to physically, when that electron flows from the negative over to the positive, it's happy, it wants to be there, we're going to rip it away from the positive, put it back on the negative where it doesn't want to be. But if we could do that every single time, then what would happen is that we would have a constant flow of electrons through that conductor. So until there's, or as long as there's a difference in potential, charges will flow. And so if you can have that magic electron mover to rip charges back to where they don't want to be, you will have a constant flow of charges. You'll have what's called a current. Now, it turns out that these magic electron movers exist. They are called voltaic cells. Okay, and you may remember these from chemistry, and I'll do a really quick one. But let's say you have two different acid baths or electrolyte baths. And here we go. I'll put this in a kind of a blue, like here, like that. You have two electrolytes. which are fluids, okay, which a lot of different fluids in there, acids or bases or salts, and we'll talk about that a little bit later. Oh, it's right there, acid, base, or salt. And inside, I'll put these in red, you have two dissimilar metals. And I'll put this one in green to show you that they're different. These are known as electrodes. And I'll put these, so, yeah. Electrode. Wow, that's really bad. Give me a second. Let's try this again. Take two. Elec. I get writing too fast, as you probably have noticed. And then the board can't keep up. Okay. These are dissimilar metals. And what's going to happen is that you will have on one side electrons being ripped off. And so this ends up having a net positive charge on this side. And then you have positives being pushed on. Now, it doesn't always have to be the electrons ripped off and positives put on. You could do the opposite. You could rip off positives, put on negatives. It depends on the metals. It depends on the electrolytes. It depends on the solutions that you have. But what you will end up having is that you will have a voltage, a difference of potential between those two. This electrolyte, electric cells, this voltaic cell is our magic electron mover. So if we connect these with a conductor, I should probably put a top on each one of these. If you have a conductor, then what's going to happen is those, so this side, you have this side being positive, this side being, hang on, I screwed that up. That side's going to be positive. Let me go back and change this. I apologize for that. I need to erase these. These are going to have negatives put on, not positives. So electrons will go on this one, or negatively charged ions will go on this one. So they're being ripped off one place on the other. So this side is going to be that negative side that we wanted. And so now electrons will flow. Go through it. And as long as we can maintain that difference of potential, we'll have that electron flow. Okay? Now, what the voltaic cell does is it does work in order to move those charges to where they don't want to be. And that's what creates that electric potential energy in those charges, so that when they flow through the conductor, we're having other stuff. So we will work on this. Again, it still obeys our law of conservation of energy. Okay? Still obeys our law of conservation of energy. Life is good. We'll work on this a little bit. And the last thing I want to talk about is actually a battery. A battery is just a combination of voltaic cells. And I'll show you a couple of those tomorrow. We'll talk them a little bit more, and we'll do some sample problems and do some more discussion. I realize it's a lot of information, short amount, but electricity, we will do a lot of cleanup. Again, this is just the bare basics of what you have to know. We're going to do a lot of cleanup in class. So come prepared tomorrow with questions. All right, everybody have a great day. We'll see you later. Bye.